give me like a thumbs up or something.
Yeah.
Okay. Great. So today I'll be presenting this paper called Learning Dynamics of LLM Fine-Tuning. It was one of the papers that won an Outstanding Paper Award at ICLR 2025. And it's an interesting paper for a lot of reasons, but one reason why it's interesting is because it's actually not a paper. I mean, there is a novelty in the paper, but the paper isn't really focused on novelty. Instead, what it's focused on, or methodological novelty, in order to like produce a different type of LLM or something like that. Instead, it's focused on trying to come up with a mathematical framework to explain different behaviors we see when we are fine-tuning LLMs. So it's focused on LLM fine-tuning and then also understanding what's going on under the hood. And it takes a really, really fine-grained approach, looking at like the impact of single updates in fine-tuning. Yeah. And so the paper itself, it focuses on, I think it really has two main things that it looks at. Like besides the math that we're going to go through later, it identifies like how a fine-tuning update, depending on the training objective, will impact a test set or a set of examples that we care about. And specifically, there's two results that it shows. Like one that, and we'll go into detail about what these mean, but one result is that when you're using a positive example to train a model, and the model is being trained using cross-entropy loss, then even in the case of LLMs, where you have autoregressive models, the objective will not only increase the probability of the correct answer, it will also increase the probability of similar answers. And then another thing that another result that this paper shows is that in the case of offline DPO, which is like a form of fine-tuning that uses preference learning, that there's a squeezing effect, or at least that's what they call it, which is that all of the probability mass can be focused on like the most likely answer after that's due to of the model before it started being trained, and that can have some downstream effects like creating specific types of hallucinations. We'll go into a lot more detail about those, but I wanted to give kind of like an overview. And so the paper is really like providing a mathematical framework for how they could justify these observations, because these observations have been around for a while, like these are known before this, and then showing like empirically with some results that these observations make sense and that they actually do occur. Okay. So as the paper states, it's about the learning dynamics of LLM fine-tuning. So first, let's talk about what learning dynamics are. So learning dynamics has a pretty like specific definition here. I feel actually like it might be better to come up with a more specific phrase for this, because learning dynamics is such a general term in my opinion, but it says it right here. Learning dynamics is the procedure can be described by learning dynamics, which links changes in the model's predictions to the gradients generated by learning specific examples. So how does the update created by certain examples change the model's predictions on some set of tests, like on a test set, we'll say. And they point out here that actually the study of learning dynamics, as it is described with this definition, has been able to explain some interesting phenomena during training, like the zigzag learning path and the formation of compositional concept spaces. I think the second one is pretty interesting, that like somehow you can use this to show that there's a formation of compositional concept spaces. Like a concept space is a space of abstract ideas, or like abstractions that are created by the model, like probably not taught, or maybe taught specifically. You know, like an abstraction could be a car when you see like a Land Rover Defender, because it's like an abstraction of what you're actually seeing. Okay. So anyway, learning dynamics has been used before to do a number of things. And then they say, but we're applying it to fine tuning, and they talk about two types of fine tuning that they argue occurs that practitioners perform right now, which is, so you get your pre-trained LLM, and if you want to fine tune it, you start off with instruction tuning, where the model learns knowledge necessary for the downstream task. So this is where you could have a data set of like expert knowledge that you teach the model on. Personally, I think it'd be really cool to be able to show that like some work on whether it's actually possible to teach the model new knowledge in this way. But anyway, like with fine tuning. And then the second thing is then there's preference tuning, where the model aligns its output to human preferences. So, you might learn the new knowledge, and that's usually through supervised fine tuning. And then the second phase is where you're using preference tuning to make the answers more like the way that a person would want them to be answered. Okay. Okay. Yeah, we will talk. But one thing I forgot to mention is that based off of the observations they make about like one of the weird consequences of learning dynamics for offline DPO, excuse me, they actually propose a simple modification to the training process that they argue improves performance. So they do have like one methodological improvement in terms of fine tuning itself, not only just understanding fine tuning. Okay, but we'll get to that. It's at the very end, and it's super simple, which is nice. So first, let's like formalize mathematically learning dynamics. So there's a lot of different, again, like it says even here, learning dynamics is an umbrella term describing how the change of a specific factor influences the model's predictions. So in this paper, they focus on how the change in model parameters influences the corresponding change in the output of the model. So F is the model, theta is its parameters. So a change in theta changes the predictions of the model. So and here's equation one. You can see that they define, they're doing this for like single step updates, and they define the change in parameters as like the gradient update that we're also used to in deep learning. So eta is your learning rate, and then this is your gradient with respect to some example xu with an output, desired output yu. And then, so that's your change in parameters, and then your change in prediction is the difference between these two values. So your previous prediction and your current prediction after the parameters have been updated. And you're always doing the change in parameters is always caused by some training set example, xu, and you want to evaluate it with respect to some other example, xo. So it's right now that they talk about like a one-to-one analysis. So you're just looking at the impact of one example on another. But I think that, and that's all of the analysis that they do and all the equations they do is formulated in this way. But I think somewhere they say like you could extend this to the batch setting where you're not just like updating on a single example. But I don't think what I think is kind of cool about this paper is that a lot of the results that they're showing, it's okay that they're not doing it at the batch setting. They're just showing like the impact of a specific example on another example. Because I think more than anything, this is interesting from the perspective of providing like an intuition on what's going on under the hood. Okay. So in equation one, like I said before, they define the change in model predictions as the difference between the output of the model before and after a gradient update. But they want to be more specific, so they define the change, this change delta F, big delta F, as actually the change in the log probabilities of the output of the model before and after the gradient update. And so they're assuming that the model outputs is performing classification, and that it outputs like a set of probabilities over a fixed set of outcomes or possible classes. Yes. And then we get into like, I think the most complicated part of the paper, and I won't go into too much detail about this, but basically they argue that for the single example, L equals 1, that the change in the output of the model can be described by, well, not argue, they show that it's proven in another paper, but like can be described by this set of 3 terms. And really it's the second two, so you have this like math cal A, math cal K, math cal G, and that's your learning rate if anyone's wondering. But so they're saying like the change can be described by these 3 terms, the product of these 3 terms times the learning rate. And the 2 terms that they talk a lot about throughout the paper is KT and GT. Now, so we won't talk too much about AT, but let's talk about KT and GT. So you can see the inputs to each of these terms. Like KT, the inputs are the training example, which is XU, and the test example, which is XO. And what KT is the like the product of their gradients to form a matrix of size V times V. Like the gradients of the logics, we won't get into that. Like the gradients of the output of the model with respect to the parameters in such a way that your output is the size of the vocabulary, or like the number of classes that you're classifying. And that means that KT is the empirical neural tangent kernel of the logic network. So I don't know a ton about neural tangent kernels. I looked it up for like a second, but like a neural tangent kernel is, it basically tells you how like how training on a specific example will change the output of another example. And but yeah, that's not a poor explanation. I'd encourage you guys to like look it up in more detail if you're interested in learning about neural tangent kernels. But they give a better intuition for this, which is like that KT can be thought of as like a model-specific similarity measure between different input examples. So you can think of this matrix as being like a similarity matrix between X0 and XU. And that's important because that means like if there's a high similarity, yeah, go ahead, Arvid.
So just asking, is this so it's sort of like a dot product in the model dimension space, right? Because we take the gradient spectrum. So the I got a bit confused when I see this. I thought it's the gradients. It's yeah, it's just some external product, but actually, yeah, it's sort of split up across the dimensions of the output, like which is your vocabulary size, but it's still like a dot product in the space of weights. So yeah, how similar are the gradients in some respect, right? Yeah.
Mm-hmm. Yeah. So like both of these matrices in the K term are of size V times the number of parameters in theta.
Yep.
And as Arvid pointed out, that means that you're taking the dot product with respect to the parameters in theta.
Yeah.
And with respect to each of the output classes. Anyway.
Thank you.
So you can think of it as like a similarity measure, and that the like the magnitude of its values determine like how much a training example will affect the test example. So if they're not very similar, then the impact of the training example could be very small, and it's due to this term KT. And then the second term, GT, is just the gradient of the example with respect to the loss. And that, as they point out, determines like the direction and magnitude of the change. So like it's this term, you could kind of think of it as like, this is the term that's telling how much to change and in what direction to change the prediction of XO. Like XU is telling, and then this term is saying how much to pay attention to that change described by GT. Very simplistic explanation, but I think it's better to stay focused on like to look at it in this way. There's a lot of complicated math that goes into proving a lot of the results here, but that's the basic intuition. And so after they've defined learning dynamics, which they do up here, and we just talked about the really granular level, which is proposition 1, then they start talking about a specific example. And then they say like, okay, so given this this equation, how does this actually play out? Like, what's the learning dynamics in different situations? So they look at MNIST, where MNIST is a data set of images of handwritten digits and from 0 to 9. And then the output is like a classification of those digits. And this chart kind of shows you what's going on under the hood. So say you have a training example, which is that XU is equal to, so that it's an image of 4, and then the output is the class 4. That's what they're showing here. So if you have a class that's identical to the original one, so like your X0 is 4, your image is 4, then this is what your updates look like. So you see that actually not all of the classes are impacted, but a couple of classes are put down, and then one is gone up. So like 4 has gone up. But also not only for identical classes, but also for similar classes. So I guess in MNIST, or for the models that the model that they're testing, 4 looks very similar to 9, and consequently, this training example also increases the probability of 9 being classified as 4 quite a bit, and decreases the probability of it being classified as 9. And then they also have like a dissimilar example where what happens is there's like basically no change. So it's saying like, okay, for dissimilar examples, this specific training example doesn't have any impact. Yeah. So it's just showing you what we talked about before, which is like if the test example is similar or identical, then you see a big change in like the target class of the training example. And then if the example is dissimilar, then you see a okay, then nothing happens. But what's also interesting about this is that like the update will also pull up similar classes. So okay, it is saying that in this example, it shows you that only the probability of 4 is increased. But actually, I think that they say, so I don't think that's a great example, but they say that like the training example also like will increase the probability of 9. So similar examples will also increase the, yeah, Arvid?
Yeah. So that by itself would just mean that if we were to update our model again, and the data set on which we update were imbalanced, say we have only 4s but no 9 in our data set, we would over time essentially suppress the 9 until every 9 would be considered a 4, right? But if we were to balance them again, it wouldn't be an issue, right? You probably just naturally have some level of confusion among them, but apart from that, it by itself, whether they are positively or negatively correlated, doesn't mean it's a good or bad thing, right?
Mm-hmm.
Yeah, thank you.
Yeah, so it's saying that like even similar examples, the incorrect probability will get increased. So yeah, that's like the first major result, and that's why I've talked about it for quite a long time, that when you're training using cross entropy loss or something like that, with I like to say with positive examples because it facilitates later on, that your training example will also like increase the probability of similar examples, even if they don't have the same don't have the same class. So like 9s will be classified as 4s, even though they're not 4s, because of this example, because they're similar. Okay. Now, learning dynamics of LLMs fine-tuning. So one thing is that all the definitions that they've given up to this point, including this proposition here, have been for the case where, for a non-autoregressive model, which is a model where there's no sequence, you're just trying to output like a class for specific examples. But with LLMs, these models are sequential. And they even say here, the sequential nature makes the distribution on different tokens mutually dependent, which is more complicated than standard multi-label classification problems. They also point out that for the learning dynamics of LLMs, that there's a lot of different ways of training them, and it's hard to find like a unifying framework to evaluate all of these different methods of training. But that's what this paper is about, like coming up with a unifying framework for estimating the learning dynamics. I'm not really going to go through. I'm not going to go through all of this. I'm happy to go through it later if you're interested in like going through this in more detail, because it doesn't really change anything, I think, from an intuitive point of view. Basically, the main thing is that like the terms to calculate the impact of the impact of an example change, and that's what all of this is describing, but not in a way that I think changes any of the intuition or the ideas behind it. So yeah, I'm not going to go through that.
Yeah, so I think they did all they did was condition the output on the observed data mask.
Okay.
It's almost like a partial derivative of sorts. So it looks a lot more complicated, but if you think about it, it's actually not that surprisingly difficult. But it was quite cool.
Yeah. They basically, the whole thing works because of causal masking in the model. Yeah. So like you can say, well, because of causal masking in the model, we can actually condition on both the input and the output for calculating the output.
Yep.
Yeah. But anyway, this term, this is the new equation. So this is how you calculate LLM dynamics. Okay. So what this part of the paper is doing is just telling you how to calculate learning dynamics for an LLM. But then here's where they start talking about doing something more interesting, where they start talking about the decomposition of the DPO loss. So calculating learning dynamics for the DPO loss, because for like standard LLMs, which is what they're talking about here, what you're doing is your training objective is to just predict the next token, to predict the next word. And that means that even though it's a sequential task where you calculate each token and sequence, it's still a task where you're performing classification at each step, whereas of the next word. Whereas in DPO, it's very different. The way DPO works is you get two outputs. So you might get like, what is the capital of France? And you might get an output like the capital of France is Paris, and the other output might be like, the capital of France is located at this longitude and latitude, and it is an amazing city or something. And then you have a label of which of the two outputs is preferred. And the training objective is trying to maximize the difference between those two outputs. And that's what you see here. So like the y plus and then chi plus is the positive example, and the y minus and chi minus is the negative example. And the difference between these two is what you're trying to maximize. And so the big thing to note here is that you're not only training with a positive example, you're training with a negative example. So you're saying there's a bad example as well as a good example. And there's two ways to improve this training objective. One is to increase this first term, and one is to decrease this second term. And so, and that has a major impact, because if you're trying, like, decreasing the second term actually affects the learning dynamics in a different way than if you're just trying to increase this first term. Maybe we'll come back to this, the stuff that I've highlighted, but yeah, because I don't want to go into too much math, and I'd rather get the intuition forward, and then we can go back to the math if we want. But okay, so like I said before, there's positive and negative examples now in DPO, and then there's another step. So we were saying, like, as we said before, the one of the big things that they talk about is like the weird behavior you see in offline DPO, like repeated phrases, like or more hallucinations. And one of the other big things is that in offline DPO, the way that these examples, the positive and negative examples, are generated is usually it's not necessarily by the model itself, and not necessarily, maybe it's by the model, but not at the time when the model is being trained. So maybe the model has changed with respect to like when the examples are collected. And so what that means is that, as I say here, both the chosen and rejected responses can come from a less likely region of the model's prediction. And the squeezing effect that we'll talk about in a second, they argue that that happens because of large negative pressure created by an unlikely prediction. So this term and this term being very unlikely, what does that do? And they say it actually has this weird effect that you wouldn't expect. So what is the squeezing effect? Let's talk about that. And then we'll talk a little bit, and yeah, what is the squeezing effect? So the squeezing effect is as follows. So you have a positive example, y plus, and you have a negative example, y minus. And then you have your most likely example of your model, which they call y star. So this would be like when you're generating a response to a question, you just take the most likely next word as the word to use. And with offline or off policy DPO, y star, the most likely response, is often not close or similar to the positive response, so like the preferred response, because it's from a different model. And so what's weird, what actually ends up happening is, because of the negative example, a lot of probability gets pushed towards the most likely example instead of the preferred example. So what happens is that, like, yes, the negative example will become less likely and the positive example will become more likely. But then, or sorry, no, not even that, sorry. What does happen is that the difference between the probability of the positive example and the negative example will increase, but then the probability of the most likely answer will also increase. And this can lead to some weird hallucinations where you see like a lot of repetition, because the whole time, neither of these answers, the probability of neither of these answers is being increased. Instead, like a different answer's probability is being increased. And the most likely answer is usually determined beforehand by pre-training or supervised fine-tuning, which means that like training with DPO can amplify self-bias. So the model already has a bias towards a certain answer for a specific question, and training with off-policy DPO can increase that bias in order, while at the same time increasing the difference between the likelihoods of these two examples. So that's off-policy DPO, and it's because like when the negative term, so this term in the DPO loss, the negative term, what it actually does is it decreases the probability of every output, except the most likely output. And that's something that's guaranteed. They have some like guarantees over here. So when the negative output is the guarantee that the confidence of the negative output is less will decrease, but also that the decreased probability mass is largely squeezed into the output, which was most confident before the update. So like the decrease in the negative output will go to the most confident, most likely output. And then there's some other trends. I find that really interesting, though. I don't know about anyone else, but like that the model chooses to put probability mass. I like my if I were to guess, I would be like, why? Or my intuition would have been that it would distribute the mass that it removes from the negative example and puts it into all the other examples equally. But instead, it puts it in the most likely example.
That was due to the attention term, right? Because the attention term is somehow related to the probability, I think, of the outputs, and I think it was bigger than the probability was higher to begin with, because it essentially means it finds a more relevant piece of information to consider, and that might be it.
My intuition is that like the gradient ascent, the weighting of how much the weights are being updated is based on how likely the thing is, and so if you're decreasing the chance of this, and this is for a high probability, then you're probably going to put more here because it's got a higher weighting in the kind of expansion when you do gradient descent.
Yeah, that makes sense. I think both of what you both saying seems correct. I know that it all has to do with the fact that we're using the softmax function to calculate the distribution at the end. So Arvid, maybe like the attention might not be specifically relevant, but maybe it is. It is interesting to me though, like that maybe like the probability mass is distributed based on the likelihood of each answer, and it's distributed like exponentially more to more likely answers. I don't know.
So
Yeah.
would it be fair to say then that if you're doing DPO, you would want one of your positive or negative examples to be close to the most likely picked by the model?
Yeah, I think or both.
Yeah. Okay.
Yeah. Okay, let's see if any of these. I told you the first two things, they see a trend. They say like one trend they see besides the one that we just described with the squeezing effect is that like higher probability examples get more certain and lower probability examples get less certain. Yeah, okay, all of this makes sense with our discussion. Okay, so that's the squeezing effect. It only happens with like, so that they're saying it happens when you're training with something like DPO where you have negative examples, and the way that you generate the examples that you train on is with a different model, or a model that's different than the one that you're training on, and hopefully likely very different, and that's what causes this issue. Okay, and then they start showing some experimental results in order to. Okay, they start showing some experimental results in order to like verify their findings. So let's look. I'm not gonna go through the experiments, like this data set, these models, and so on, because I think I can explain it without that, and that's a little bit clearer. So let's see how I do. So if you guys remember, unless I need a reference, if you guys remember the first result that we talked about, the big one, was that the model not only increases the probability of, when you're doing supervised fine-tuning, the model doesn't only increase the probability of the correct answer, but it will also increase the probability of similar inputs for that answer. And that's something that they argue that you see here. So you can see that, like, okay, the blue line is the correct example. And then you have all these other examples that what they say is that they argue that they are all similar in some way or another, because they're like all different answers to the same question. And so they should all be pretty similar. And they say like, okay, and that's what you see, that like in the beginning of training for supervised fine tuning, not only is the probability of the correct answer or the preferred answer going up, but also the probability of all of the other examples which they argue are similar. And then they say, well, but after a while, like the impact of this training example becomes smaller, because they say, like, as the difference between the correct answer and the learned answer becomes smaller, so does the impact of that answer. So they get pulled up less, and they actually like decrease in value. So that's check for what they described. And then also they have these two examples here. So that's, I'm looking at figure 3, the leftmost plot. Now we'll look at the second to leftmost plot. They have these two generated examples here, y plus that y dash. Those, they argue that both of those are completely different answers, and that's because they're just randomly generated jumbles of words. And you can see that their answer, that their probability, their likelihood goes down over time. So yeah, so that's showing that, like, for dissimilar examples, there's no impact on the likelihood from training. It just keeps going down. Again, check. And then the next example that they give is, okay, I need to go back to this one, so I'm not going to remember otherwise. Okay. So this next one is, like, you have two different responses. One is a test set response, a positive test set response, and one is a training set response that's not the correct one for this question. And what they show is, like, as you're training the model, as like the likelihood of the training set response for another question also becomes likely for that question. So if your question was like, what's the capital of France? And then the answer is it's Paris, but there might be another one that says it's St. Petersburg. If that's in your training set, the likelihood of that will also go up. And that's in line with what they were saying that about how similar examples likelihoods go up. So that also could point to why you might see, like, responses from training set examples at test time, because their likelihood goes up during training time. Won't talk about this because I talk about it later. And they say, one last result, sorry, is that they calculate the accumulated influence of, like, specific examples on each other using this heat map during training. And so blue means similar and red means dissimilar. And one result that's just kind of like an interesting observation is that all of these inputs are generated by ChatGPT, like the ones that I'm scrolling over with my cursor now. And if you look at them, they're all considered similar to each other. And that's why they say here, probably an LLM has its preferred idioms or phrases, which could be considered a type of fingerprint. So like this type of analysis maybe would show similarity based on learning dynamics. Maybe it's a way of figuring out how to, like, identify a specific model. Maybe. Okay. Yeah, Arvin?
Maybe that is how DeepMind is distinguishing between different LLMs, as you mentioned earlier.
Yeah, maybe. I feel like, so in order to do this, you have to have access to the gradients of the model. But maybe it can do it for its own LLMs or something like that. Okay. Learning dynamics of off-policy DPO. Okay, so we've talked about, like, how basically similar examples also increase in probability. the response for a specific example increases in probability for similar examples. That's what this whole thing was about. And now we're going to talk about the squeezing effect, which they talk about a lot. So the first part of the squeezing effect, and this is an observed impact that it's already been documented for DPO, is just like the probability of all responses, training responses, goes down. And you can see that here. So if we look at figure 4, the leftmost, you have the preferred response, or the positive response. And the dark blue line is the actual positive response. And you can see it increases a bit at the beginning, but then it just starts going down over time. That's what people see. And then the probability of similar responses goes down as well. You'll notice that the probability of the preferred response goes down slower than the similar responses. And then also you have the negative example. So like the most deep, or the most orange line is the negative example. And you see that the difference between the two, like the negative example goes down the fastest, but also similar examples go down. And in general, like all of them go down, but like the positive examples go down more. The positive similar examples go down slower than the positive negative examples. So you can see that by like the orange lines going, like starting higher basically, and still going down more at the end. And overall, the impact is that like the goal of the training objective is to increase this distance as much as possible between the blue and the orange line. And you can see that it achieves that goal, but in doing so, it decreases the probability of everything, which is what you can see on the rightmost, except for the most likely response, which is the black line. So the only thing here, not even the similar examples, the only thing here that's increasing is the most similar response, and that's what these results show. Yeah. So yeah, that's like the second result that we were talking about. And then, okay, finally, all right, the last result that they use is, or sorry, not the last result. The last thing that they do is propose like a solution or a modification to the off-policy DPO that can mitigate the squeezing effect. And it's super simple, which is that when usually you train a model using supervised fine-tuning before you perform reference learning. So if you do that, then you add the positive and negative examples to the training set for supervised fine-tuning, with the idea that they both become more likely. And they argue that the whole reason why this squeezing effect happens is because both of the positive and negative examples in off-policy DPO are far away, like less likely in the model. So if you put them in the supervised fine-tuning, then they'll be more likely, which should stop the squeezing effect from happening as much. And so the question is like, does it actually happen? Does that actually happen? The short answer is yes in their experiments. So if we go to the rightmost plot, you can see the likelihood of the argmax response during DPO, and it does always increase. So it's always increasing. This is the dashed and dotted, like dotted, that line in the middle, the black line. That's when DPO starts. So you can see that like during supervised fine tuning, the most likely response increases for both of them, but then during DPO, it decreases at the beginning for their method, which is the orange one, the one where they train on the examples at first, and then it doesn't increase as much. So it mitigates the impact of this argmax issue. Yeah, I guess I won't even tell. All the other results are just kind of talking about the same thing. So yeah, that's that. Oh, and then what the other result for this is that they train models using both of these methods. So the normal method where you don't put in the DPO training set during supervised fine tuning, and another method where you do. And then they ask ChatGPT and Claude to tell you which of the two responses are preferred. And they do this for like a number of epochs after training on DPO, with the idea that their method, and it's the win rate again. So higher is better, and their method should be preferred more often than the other one using these two LLMs, and you can see that it is. So like the win rate increases over time. Before DPO starts, they have a win rate less than 50%, which means that both these LLMs like their model less, their proposed model less, but as it goes on, they like it more. I did feel like this is a bit of a weird one because they're using LLMs as a judge, and I'm wondering, like, are they sure that the LLMs these are good judges, and so you can trust these results to say that like our method improves performance in this case? I don't know if anyone has an opinion on that. Anyway, that was kind of like a whistle-stop tour of the paper and the results. The main thing to take away from it is, I think, yeah, Shay?
In your experience of going through these papers and breaking down the nits and bolts so that some of us who aren't as experienced reading these papers can understand the logic, what stands out to you the most about this paper? In the beginning, someone mentioned it was outstanding because of the aspect of novelty and how they've looped together these frameworks to create a finer tuned framework for LLMs.
So for me, the thing that stands out the most, because it's common with the previous paper that we were looking at, is the use of like additional examples from like an evaluation set and then model gradients in order to understand the impact of training set data. Because it seems like, so both of this paper and the previous one used those two, had those two common things. And so for me, I was like, well, these are both outstanding papers. They both have these two common elements to evaluate like training set data point impact. So maybe we'll start seeing more stuff like that in the future. That was the thing that stood out to me the most as like a higher level observation. Yeah. So I think more the first thing that I would try to take away from this paper is just this definition of learning dynamics, because it seems like it's one that's used in the literature, and maybe it's, to me, learning dynamics wasn't clear before I read this paper. So it's it's specifically like how the change of a specific factor influences the model's predictions, and this idea of like change in parameters changes the model predictions, and like doing an analysis around that. So yeah, that would be the first thing I would try to take away. But yeah, that's the paper. Happy to answer any other questions if you have them.
Can you explain again how they propose a method to remediate these problems?
Yeah. So they only propose a method to alleviate the squeezing effect.
Yeah.
And it's down here. I mean, it's just written in a couple sentences. But they argue that, and I actually think they argue this without, if I were them, I would have like a plot that shows that there's like, that both, so they argue that the negative and positive examples in off-policy DPO are unlikely to the model. And what that does is it causes the negative term in DPO to decrease the probability of everything except for the most likely term, the most likely output. And so their solution is like, well, if the reason why this happens is because the positive and negative examples are unlikely for the model, when we're fine-tuning, we're performing supervised fine-tuning before DPO, we'll put those examples into the supervised fine-tuning training set. So at least at the beginning of training, they're both likely in order to mitigate the impact of squeezing effect.
I see.
I was actually wondering, I mean, maybe it's just too much, it's computationally too much, but it's like, I thought they were going to do something with the most likely example, where they also maybe have a negative term for the most likely example.
Exactly. So some counterbalance flow or some masking of flows or something. Yeah.
Yeah.
So thank you.
Yeah.
Very, very good presentation. It helped me a lot to understand it.
Yeah. It's a bit hard. It was also quite hard for me to wrap my head around how to present this, but hopefully you guys take some stuff away from it.
To explain some of the variables a bit better, like the y plus, y minus. I think it was never particularly well described, as one is a positive example, one is a negative example, and yeah.
Absolutely. Another thing is I didn't see they touched it, is that you could actually, if you are doing DPO, the data set you're about to use DPO on, you could check how likely it is in the model before you use it. So only use examples that are, or realize, then go, okay, it's too far. We need to do some fine tuning with our samples before we use these ones or something.
Yeah, that could be cool. Just like and they already kind of have a tool for it, right? Because they have this, although it's a matrix, so you want to boil it down to one number, but this, where is it? No. This KT matrix over here, which is like the similarity matrix between two examples.
Yeah.
Maybe they could use that to do what you're talking about.
Good point.
There's a paper from 2018 on neural tangent kernels, if anyone's looking for a paper to present. Like I think it's like the one that introduced it. If anyone's looking for something like that.
Thanks.
And then this paper, Ren et al. 2022, they cite it a lot, so maybe that's another paper if anyone's looking for a paper. Yeah. Cool. Well, if there's no more questions, I'll stop presenting. Thanks everyone for coming, and we're not doing paper club next week, but we'll be doing paper club again in 2 weeks. So I hope to see you there.
Fabulous. Thank you.
Thanks a lot. Great presentation.
Thank you.